So please don't skip ahead. I know the p-value's what you want to see, but I will always be doing my homework in this class because it seems to take forever, but then I understand it and it feels good and I get the little green checks. It makes me happy. So here is the same problem we were just working with. How far have we gotten? Well, we've talked about the idea of could they be independent? Could your gender be independent of which ice cream flavor you like? And so what did we do? Well, we talked about under independence, how could we find these expected values? And I put the rest of the expected values on there. If you can't get these numbers, that's important. You need to play with it until you can find them. How are you going to do it? For each cell, you're going to look at the observed table and take the row total times the column total over the total and put it in there. Now, when we start this, students often feel like we're doing something totally different. But after you play with it a little bit, students like the chi-squared test better than the others. Why? I don't know. Something about you can just see what's happening. Let's see if our expected values make sense. All right? This is the expected values for chocolate, vanilla, cookie dough, and other for males and females. And we can see each of these numbers is pretty close. Should they be? Well, we had pretty close to the same number of males and females. So we're expecting these numbers to be pretty similar, and they are, all right? Slightly higher for the females because there were more females, okay? And you'll notice also higher for the places that were most popular. Cookie dough was the most popular, and so it has the highest expected values. Yeah, this makes sense, okay? A quick way to check whether you've done your expected values correct on the test is to add these guys up. It should come up to the same as what you had before. And there's a little bit of rounding error. I'm only putting 2 decimals on here because I have to write big because my chalkboard is small, even with the camera zoomed in. So this comes out to 112, I think it's 112.3 or something because of rounding. But close enough to make me feel like I'm okay with how I'm doing this expected value. I must have the equation right to get these to come out pretty close. This one actually comes out to 18, which is nice. Okay? Now, these were our expected values. What's next? What's next in our hypothesis test? And we haven't even written out the null and alternative yet. We're going to get there in a minute after we've built these tables. For chi-squared tests of independence, this is how it works. You have your observed table, you make your expected table, and then you make your chi-squared table. It sounds like a lot of work. Okay, it is a lot of work. Let's find our partial chi-squareds. All right? Let's find some room on the board to write partial chi-squareds. Anywhere. Let's put it right here at the bottom of the board. Chocolate, vanilla, cookie dough, and other. And I'm talking males and females. If I write that low on the board, does it show up? It does, except I made my columns all sorts of messed up. That's okay. Let's go with this guy. Why? Because I wrote the cell really big. What is my chi-squared for this? In other words, I observed 8 people. I expected to get 8.84. How far off is that? Well, to get this guy, I'm going to call him my chi-squared for the male other, which spells Mo, and that's kind of cool. I'm going to take 8 minus 8.84. Okay, that's how far apart they were. I'm going to square it. Why am I squaring it? Because in the end, I'm going to want to add all these guys up. And I can do that if I'm talking about variances. We don't do that with standard deviations or with errors. Before, when we had a z-score, we were only doing it once. Now we're going to do several chi-squareds all at the same time. Okay? Divided by, it's the square root of the expected squared. Why are we using the expected instead of the observed in the error? Because we want this error to have the best value that it can. And this expected value is what we expected to have happen if it was truly independent. So I'm going to put 8.84. Now, technically, I square rooted it and then squared it, but they just canceled out, right? So what do I get? 8 minus 8.84 squared divided by 8.84. 0.0798. 0.0798. Okay, well that's interesting. Let's see if we can get this guy. What would he be? He's going to be 10 minus the 9.16. 10 minus 9.16. I'm going to square that and divide by my 9.16. What do I get? 0.077. Okay. If you can't get these numbers, if you can't pause the video and get these same numbers, that's a problem. Make sure that you know how to get expected values and how to get chi-squareds, and the rest is going to be easy. Trust me, I promise. The first two videos are all the hard work, and then we do fun stuff. Let me get this guy. He's going to be 50 minus 41.26. I'm going to square that. Now, you may notice sometimes I'll accidentally switch these guys. Instead of observed minus expected, I might do expected minus observed. Because we're squaring it, it doesn't matter. Okay, the squaring it will turn it positive no matter what you're doing. Chi-squared values are always positive. So this part, it doesn't matter if you switch. Now, if you put the observed down here instead of the expected, that matters. It's got to be expected right here. So I just did 50 minus the 41.26. I squared it. Now I need to divide by expected, which is 41.26. I get 1.85. And now I'm going to keep going and fill out the whole table. It's going to take me 8 calculations. That's okay, I can do it. But I'm not going to waste your time. Let's pause it and fill it out. So here we go. Here's our numbers filled out. If you can't duplicate these numbers, that's an issue. Make sure you know what I'm doing. All right? Now, these are chi-squared values. They are a measure of how weird was an observation. Okay? Just like the z-score said, how far away were we from what we expected? These chi-squareds say which one's weirdest. And looking at them can actually give us information. Which observations were not weird? Those are ones that are close to 0. Close to 0 means the observed and expected were about what we thought. And if you look over here for the vanilla ice cream, these are very small chi-squareds. Why? Well, we expected 35.9 and we got 35. Yeah, that's pretty close. We expected 37.14 and we got 38. Yeah, that's pretty close. So in other words, for vanilla, the male-female ratio, it's not surprising. It doesn't seem to have a relationship. But which ones are big? Look here, 1.85 and 1.7. Those are big. Over here, 1.8 and 1.9. Those are big. Big chi-squareds. And what do I mean by big? I'm looking at all the numbers. Which numbers are the biggest? That tells you where the weirdest stuff was. Cookie dough was weird, and chocolate was weird. Why? Well, for cookie dough, we had a lot more men than we thought, and we had a lot fewer women than we thought. Let's look at chocolate. For chocolate, we had a lot fewer men than we thought, and we had a lot more women than we thought. So it appears to be that some of these cookie dough lovers we expected to like chocolate, and they didn't. They liked cookie dough instead. No particular reason. I made up this data. Okay, I think chocolate ice cream is great. I'm not saying anything negative about chocolate ice cream. In fact, chocolate's better than vanilla, which is just no flavor. So, right? This is what we've got here as a measure of how different those things are. So, what we've done so far is look at the work to calculate the thing. Let's actually try to put our hypothesis test together by erasing all the equations. If you don't already have these in your notes, shame on you. Wait, don't erase me. I'm an important equation. Ah! Go away. So, here's the kind of hypothesis test we're talking about. We have a null and an alternative. Now, you might be tempted to do a null based on proportions. I want proportion 1 to equal proportion 2 to equal proportion 3 to equal proportion 4. And you actually could do that. But imagine if my table was 10 by 16. Do you know how many different proportions you would have to put in your null hypothesis? That gets to be a headache really quick. So let's simplify this. Our null, we're going to use words. The null hypothesis is going to say the proportions are equal means that whether you're male or female doesn't relate to what ice cream you prefer. In other words, gender is independent of ice cream preference. It's important that you recognize this sentence says the same thing as the proportions are all equal. Okay? It's independent of the ice cream preference means the proportion here and the proportion here, it doesn't matter. Are you talking male or female? The proportion really doesn't matter, okay? Because the males who like chocolate and the females who like chocolate are equal, and the males who like vanilla and the females who like vanilla are equal, okay? We're talking independence. And when we get to regression, we're going to use the same kind of null and alternative. So get used to it now. If the null says gender is independent of ice cream preference, what was the alternative going to say? It's going to be the opposite. Gender depends. Wait, whoa, okay. Mathematically, what I'm about to write won't matter. Gender depends on which ice cream you like. But that just sounds weird. If I choose cookie dough ice cream, I start to turn more manly. Well, yes, that's actually true. I'm going to write it the other way around. Ice cream preference. Ice cream preference depends on gender. Does it matter? Mathematically, no. But that just looks like a lot nicer sentence than what I was about to write. Okay, so there's our null and alternative. Null said independence. Now remember, we assume the null is true when we start a hypothesis test. And that's why we could do these. Because the null hypothesis we thought was true, and so we used that probability of A and B rule, because we had independence, to get these values. And now we got these chi-squared. So alpha, we can still use 0.05. And now we're ready to calculate our final chi-squared value. What do? We add all those guys up. And I just happen to have that on my computer, 7.57. Is that a big chi-squared or not? We're not talking the normal distribution anymore, right? Remember, it got squared. When you square, things always have to be positive. So the chi-squared starts at 0 and then tails off. It's a skewed distribution. So the bad news is you can't think of the normal distribution when you look at chi-squared values. The good news is the chi-squared test is always right-tailed. Because if you had two tails and you square it, then your left tail and your right tail become the same tail. So chi-squareds, you don't have to worry about two-tailed, left-tailed, right-tailed. It's always right-tailed. But is that 7.57 large? Well, I think our time on this video is getting pretty large. Woo, 12 minutes, okay. So let me do one more thing, and then we'll start a new video, and we'll talk about degrees of freedom for the chi-squared, okay? The last thing I want to talk about is, well, I want to talk about degrees of freedom now, but we'll do a chi-squared table in the next video. Degrees of freedom says how much of this data is random if I know the total. So if I told you that there were 112 men in the study, would you have known this number without any other data? And the answer is no. You'd have to know the 19, the 35, and 50. But then this 8, you could just figure that out by taking 112 minus the others, right? And this 116, if you had these guys, you wouldn't need him. And if you had these totals, you don't need him. How much of this table do I have to give you if I give you the totals and you can fill in the rest? Well, the answer is that much. So what's the rule for degrees of freedom? Degrees of freedom, it's how many rows you have minus 1 times how many columns you have minus 1. For math people, they want the equation. There you go. For picture people, here's what you do. You look at your table, you erase a row, you erase a column. How many squares are left? 3 squares. So my degrees of freedom are 3. We'll start a new video, and we will talk about the chi-squared table.